Swayam Prabha. Digital India. Educated India.
Welcome friends to this week 6 or module 6 of lectures of NPTEL online certification course of environmental soil chemistry. And the topic of this module or this week is basically kinetics of soil chemical process. Now, the kinetics of soil chemical process are very important if you want to understand different reactions which are going inside the soil. So, soil is a heterogeneous mixture, as you know, it is basically composed of different inorganic chemicals as well as organic compounds and a multitude of different types of reactions and basically chemical reactions are going on inside the soil system. So, to understand the dynamics of those chemical reactions, their rate, you need to understand the kinetics of soil chemical process. Soil chemical processes will determine the rate of reaction which will basically govern different soil processes like hydrolysis, like dissolution, like crystallization, like ion exchange. So, it is imperative that you should learn and understand the kinetics of soil chemical processes if you want to efficiently use your knowledge of environmental soil chemistry. So, in this week we will be basically talking about these concepts. So, first of all we will be talking about rate limiting steps and time scales of soil, and then chemical reaction and rate laws. Then we will be talking about the determination of reaction order and rate. Then we will be talking about constants and kinetic models. Then we will be talking about kinetic methodologies and multiple site models. We will be talking about effect of temperature on reaction rates, and finally, we will be talking about kinetics of important soil chemical processes. So, these all important aspects will be discussed in this module. So, today we will be basically in this first lecture we will be focusing on rate limiting steps and time scales of soil, and if time permits then we will also talk about chemical reaction and rate laws briefly. So, let us start with the first let us start with the question that why it is important to study the soil chemical kinetics. Now, soil chemical processes are very much time dependent. Different processes takes different amount of time to occur. Now, to understand the dynamics of interaction of soils with different metals, oxyanions, radionuclides, pesticides, industrial chemicals and plant nutrients, and to predict their fate with time, a knowledge of the kinetics of these reactions is very important. There are several heavy metals or trace metals which are present in the soils. Oxyanions are also present in the soil, radionuclides are also present in the soil. Pesticide, which is an important organic fraction which is added by different anthropogenic activities, industrial chemicals and plant nutrients. So, these are having a dynamic and complex interaction with different soil solid and soil solution. So, to understand their interaction and to know what is their fate with time. So, that means where the metal will go from one point of time to another point of time. So, and where they will deposit. So, these fates to identify this fate of these different elements or different chemicals, the knowledge of this kinetics of these reactions are very important. Now, The first we will be talking about rate limiting steps and time scales of soil chemical reactions. So, a number of transport and chemical reactions can affect the rate of soil chemical reactions. So, the slowest of this transport process will limit the rate of a particular reaction. So, the actual chemical reaction which we denote by CR in short at the surface in case of for example, in case of adsorption, adsorption is a surface phenomena. So, the actual chemical reaction at the surface, for example, in case of adsorption is usually very rapid and not rate limiting. And basically this transport process included different 6 different processes. So, the first process is transport in the solution phase, which is basically rapid and in the laboratory can be eliminated by rapid mixing. So, you can see here this is one denotes this first process, that is transport in the solution phase. Okay. So, soil chemical reaction involves the transport in the solution phase, which is basically very rapid, and in the laboratory when we basically mix the soil with some chemical, liquid chemical with rapid mixing, then it will resemble the transport in the solution phase, as you can see here. So, the second process is known as the transport across a liquid film at the particle liquid interface, which is also known as film diffusion, and this is basically denoted here. So, the first one, that is transport in the solution phase, is denoted by E1, whereas the transport across the liquid film in the particle liquid interface is denoted by these 2. So, this is basically particle and liquid interface, and through this particle liquid interface the transport process is going on. So, these 2 are the important processes. Apart from that, the third process is transport in liquid film macropores. So, in the soil there are 2 types of pores, one is macropores, another is micropores. So, macropores are those pores which are having diameter of greater than 2 nanometer, and those pores which are having diameter of less than 2 nanometer are known as micropores. So, transport in, so the macropores are sometimes liquid filled or water filled. So, when the transport occurs in the liquid filled macropores, of all of which are non-activated diffusion processes and occur in mobile regions. So, transport in the liquid filled macropore basically represent non-activated diffusion processes and occur in mobile regions. So, non-activated means we do not need to produce any external energy to facilitate that diffusion. So, this is called non-activated diffusion process, and basically it occurs in the mobile region. So, you can see this is basically denoted by 3. So, when the liquid in the first process is basically generated in the liquid phase, in the second process it is basically occurring in the liquid interface, and in the third process, that is the transport in the liquid film macropores, it is basically going inside the liquid film macropores. The fourth one is known as the diffusion of a sorbate along a pore wall surface, that is called surface diffusion, and this is basically denoted by 4. So, if we consider this as a pore macropore, so the diffusion of a sorbate along pore wall surface is called surface diffusion. So, you can see this is basically diffusing along the pore wall of the surface. So, it is an example of surface diffusion. The fifth one is diffusion of sorbate occluded in the micropores which are less than 2 nanometer, that is called pore diffusion. So, if this is considered as a macropore, if this is a macropore, this is an example of micropore. So, soil contain both macropores and micropores. Macropores are having a diameter of greater than 2 nanometer, whereas micropores are having a diameter of less than 2 nanometer, and this diffusion is another transporting process where in the diffusion in the micropores is another important transporting process in the soil, and basically the diffusion occurs for sorbate which is occluded in micropores. So, basically occluded means it is basically attached to the micropores. And the sixth one, the final one, is basically diffusion process in the bulk of the solid, all of which are activated diffusion process. Now, you see here, this is basically the solid phase. Now, if the diffusion occurs inside the solid, it is basically called the diffusion inside. So, it is basically an activated diffusion process. You need to put some energy to make it happen. So, this is an activated diffusion process in the bulk of the solid, which basically this is another important transportation process in the soil. So, pore and surface diffusion. So, we can see here there is macropore diffusion, another is macropore surface diffusion, another is micropore surface diffusion, and finally, we are getting the bulk solid diffusion. So, pore and surface diffusion can be referred to as interparticle diffusion because it is occurring in between the particles, whereas the diffusion in the solid is known as intraparticle diffusion. So, because the diffusion whatever is going on is basically inside the particles. So, these are the 6 different transport processes which are occurring inside the soil system. So, this is again a bigger picture of this thing. This is basically transport in the soil solution. Now, we can facilitate this by mixing in the laboratory, by rapid mixing in the laboratory. The second is basically transport across a liquid film at the solid liquid interface. The third one is the transport of a liquid film macropore. Fourth one is basically the diffusion of a sorbate at the surface of the solid. Fifth one is diffusion of the sorbate occluded in the micropore, and the sixth one is the diffusion of the bulk of the solid. So, these 6 different processes are basically governing all types of movement in the soil inside the soil. Now, so the soil chemical reactions, they can occur over a wide time scale. As I have told you at the beginning of this lecture, the soil chemical reaction occur over a wide time scale ranging from microseconds and milliseconds for ranging from microseconds and milliseconds for ionization, ion exchange and some sorption reactions, to years for mineral solution and mineral crystallization reaction. Now, this is basically very clear from this graph that if you put the time scale in the x axis, and you can see that ionization, ion exchange and to some extent sorption is very rapid process. Okay. However, the range of sorption varies widely. Now, in case of also gas water relationship, it is basically takes hours to days. Multivalent ion hydrolysis also takes from minutes to basically sometime in years also. However, this mineral solution as well as mineral crystallization is a very slow steps, and they basically take years for completing these mineral solution and mineral crystallization reactions. So, these reaction can occur simultaneously and consecutively too. Okay. So, these are this is the variation in time frame for different chemical reaction which are occurring inside the soil in the soil system. So, the type of soil component can drastically affect the reaction rate. For example, sorption reactions are often more rapid on clay minerals such as kaolinite and smectite than that of vermiculitic and micaceous minerals. Why? Because this is because due to the availability of sites for sorption. Now, you might be wondering that where there is a sorption site for kaolinite. Now, in case of kaolinite, although they do not have any internal site for adsorption, kaolinite has readily available planar external sites. So, as a result of that, they can adsorb different types of different types of compounds or ions. Now, smectite also has it's a huge internal site because it is highly expanding in nature. So, these sorptions reactions basically are very rapid in these kaolinite and smectite type of clay minerals, and then can take seconds and milliseconds to execute this rapid sorption process. Now, in case of vermiculite and mica, they have multiple sites for retention of metals and organics, including planar, edge and collapsed interlayer sites. However, sorption and desorption reaction on these sites can be slow, tortuous and mass transfer controlled. So, they are basically, in case of vermiculite and in case of mica, their interlayer space is almost collapsed because of the presence of very small cation, that is potassium. As a result of that, their sorption and desorption reactions on this type of soils can be slow, tortuous and mass transfer controlled. Now, apparent equilibrium may not be reached even after several days or weeks. So, you can see what is how this time frame is differing from kaolinite and smectite to vermiculite and mica. Now, sorption can involve 2 or 3 different reaction rates. One is high rates of exchange external site, second intermediate rates on edge sites and low rates on the interlayer sites. So, depending on what type of site it is, either it is external site or internal site or edge, the rates basically varies. Okay. Now, in case of kaolinite, these all the surface are almost external. So, obviously, they show high rate of reaction. Okay. So, or high rate of transport. Now, let us discuss another important aspect, that is the chemical kinetics, and also we will be discussing about the kinetics also, general kinetics also. Now, chemical kinetics can be defined as the investigation of chemical reaction rates and the molecular processes by which reaction occur where transport is not limiting. Again, it is very important that it is basically the investigation of chemical reaction rates and the molecular process by which reaction occur where transport is not limiting. So, given transport is not limiting, it is basically the rate of reaction which is occurring inside the soil, whereas kinetics is the study of time dependent process. Okay. Now, it is difficult to study the chemical kinetics in case of homogeneous solutions, and when the when one studies heterogeneous systems such as soil components and particularly soils, which is the difficulties are very much increased. Given that the chemical kinetic study in the homogeneous system or homogeneous solution is difficult, it will be much difficult in case of heterogeneous system like soil. So, it is extremely difficult to eliminate the transport process in the soil because they are mixture of several inorganic and organic absorbers. So, it is also very difficult to eliminate the transport processes. So, these are some of the consideration when we talk about the chemical kinetics. Now, the rate laws, there are two important reasons for investigating the rates of soil chemical processes. What are those two reasons? The reasons are, first of all, to determine how rapidly reaction attains the equilibrium, and to infer the information on reaction mechanism. So, not only to determine the rate of reaction, but also the information on reaction mechanism we need to investigate the rates of soil chemical process. So, one of the most important aspects of chemical kinetics is the establishment of a rate law. Okay. So, we will be discussing now the rate law. So, What are the rate laws? So, by definition a rate law is a differential equation. Okay. So, if we consider this reaction where these two are the reactants and these two are the products. So, the rate of the reaction is basically proportional to some power of the concentration of the reactants A and B. So, these are reactants A and B. So, the rate of reaction will be proportional to some power of the concentration of both A and B or other species like C or D etcetera in the system. Now, here you can see we are using small a, small b, small y and small z. These are basically stoichiometric coefficients. We have defined stoichiometry previously. Now, the power to which the concentration is raised may equal to 0 in case when the rate is independent of that concentration, even for reactant A or B. So, sometime when the rate is independent of the concentration of the reactants, then the power of the concentration may be equal to 0. So, let us see the laws. So, you can see here rates are expressed as a decrease in reactant concentration or an increase in product concentration per unit time. We will be seeing this example very frequently. So, again the rate in case of rate laws, the rates are expressed as a decrease in reactant concentration. So, it is negatively signed and an increase in product concentration per unit time. So, for the previous equation which you have just saw, the rate of reactant A above which has a concentration at any time t is basically can be expressed like this, and a negative sign says that is decrease in reactant concentration. So, while the rate with which the product Y is generating having a concentration of this Y bracket at time t is basically dy plus dy by dt, because this is an increase showing the positive sign showing the increasing process, and this negative sign is showing the decrease in the reactant concentration. So, the rate expression for this equation 1 is basically can be expressed in terms of dy by dt equal to minus dA by dt, which can be represented by this, where k is a rate constant, alpha and beta are the order of the reaction with respect to reactant A and reactant B. Now, this alpha is known as the partial order for A and beta is known as the partial order with respect to reactant B. Now, these orders are experimentally, remember that these orders are experimentally determined and not necessarily integral numbers. Okay. So, from the equation 1 where A and B is reacting to produce the Y and Z, then using the rate laws we can define the rate of change of the reactant concentration and rate of change of increase in product concentration by using this equation, where k is basically rate constant and A and B concentration having the power of alpha and beta, where alpha and beta are the corresponding partial order. Now, one thing is important to remember, that the sum of all the partial order, that is alpha, beta etcetera, is the overall order n and may be expressed as n equal to alpha plus beta. So, the overall order n can be calculated by summing up all the partial order of the reactants. So, once the value of alpha, beta etcetera determined experimentally, that the rate law is also defined automatically. Now, reaction order provides the information, only information about the manner in which the rate depends on concentration. Now, order does not mean the same as molecularity, which concerns the number of reactant particles entering into that elementary reaction. Now, what is elementary reaction? Now, elementary reaction is one in which no reaction intermediates have been detected or need to be postulated to describe the chemical reaction on a molecular scale. So, we just assume that two chemical reactant react together to form a product. So, that is an elementary reaction. Now, an elementary reaction is assumed to occur in a single step and to pass through a single transition state. Now, here in this reaction of two reactants A and B and forming the final product of Y and B, Y and Z, we are basically considering these as an elementary reaction, and here alpha beta are the partial order which basically sum up to produce the overall order of n. Now, rate laws have three major purposes. What are those three major purposes? First of all, they assist in assist one in predicting the reaction rate. Secondly, the mechanisms can be proposed using the rate laws, or chemical mechanisms can be, reaction mechanisms can be proposed using the rate laws. And thirdly, reaction orders can be ascertained using the rate laws. So, these are the three major aspects or utilities of rate laws. First of all, assist one in predicting the reaction rate, second is to predict the mechanism, and thirdly reaction orders can be ascertained. Now, there are four types of rate laws that can be determined for soil chemical processes. One is mechanistic rate law, another is apparent rate law, third one is transport with apparent, and the fourth one is transport with mechanistics. So, we will now see what are the difference between these four different rate laws. Okay. Now, the first one is the mechanistic rate laws. Mechanistic rate law assume that only chemical kinetics are operational and transport phenomena are not occurring. So, there is no transport, only the chemical reaction are operating or chemical kinetics are there. So, that is why it is called mechanistic rate law. Now, it is difficult to determine the mechanistic rate laws for most of the soil chemical system due to the heterogeneity of the system caused by different particle size, porosities and types of retention sites. So, if we do not consider the transport phenomena and only consider the chemical kinetics, it is difficult to express the rate law because of these three confounding factors. One is particle size, variable particle size in case of soil, porosities, macropores or micropores, so variation in the porosity also, and the third one is also types of retention sites. So, this is called the mechanistic rate laws. The second one is apparent rate law. Now, in the apparent rate law, it basically includes both chemical kinetics and transport control process. So, it basically consider both chemical kinetics and transport control process. So, the mechanistic rate law did not consider transport control process, however, apparent rate law consider the transport control process along with the chemical kinetics. Now, apparent rate laws and rate coefficients indicate that diffusion and other microscopic transport processes affect the reaction rate. So, obviously, according to these apparent rate laws, these reaction rate is dependent on the diffusion transport process as well as other microscopic transport processes, because if this diffusion of the chemicals are not occurring, then the chemical reaction will not happen. And also soil structure, stirring, mixing and flow rate would affect this kinetics in case of apparent rate laws. Okay. So, this is the second type of rate laws. The third rate law is called transport with apparent rate laws. So, it is basically the transport with apparent rate laws basically focused on or emphasized on transport phenomena, and it basically assumes a first or say zero order reaction. Okay. Now, transport with mechanistic rate laws, this is the fourth and final one. it basically describes simultaneously the transport control and chemical kinetics phenomena. So, it basically define both simultaneously both transport control and chemical kinetics. So, from the physics point of view, they basically define this transport control process, and simultaneously from the chemical kinetics also, chemical point of view also, chemistry point of view also, they express the chemical kinetics. So, these four different types of rate laws which we generally apply. Now, before discussing the next phase in details about the rate laws, we need to understand the difference between first order and second order reactions. So, a first order reaction rate depends on the concentration of one of the reactants. So, the rate of reaction here basically depends on the concentration of one of the reactants. However, a second order reaction rate is proportional to the square of the concentration of a reactant or the product of the concentration of two reactants. So, basically in case of first order reaction, this rate depends on the concentration of one of the reactants. Here products are not considered. However, in case of second order reaction, the rate is proportional to the square of the concentration of a reactant. So, in case of reactant, if there is a if the concentration of the reactant, if you take a square, the reaction rate will be proportional to that concentration square, or the product of the concentration of the two reactants. So, if there are two reactants A and B, then the product of the concentration of the two reactants will be considered while defining the second order reaction. So, friends, let us wrap up this lecture here, and in the next lecture we will be talking more about the different types of rate laws and how we can calculate that. And I hope that you got a basic overview of the kinetic process and why it is important to learn different chemical kinetic processes in the soil. And let us wrap up the lecture here, and in the next lecture we will be talking about different rate laws and also their implication and how to calculate different rate laws using different methods. Thank you very much.